Hey there, I just wanted to do a quick follow-up video to the binomial pricing model we did a couple weeks ago. And this is more for the sake of completeness, but I want to go back to that and just show quickly how to calculate implied volatility using this model, assuming again you know the option price. I'm just going to breeze through it pretty quickly because we've done similar things in the past and I just don't want to keep repeating the same topic. But again, for the sake of completeness, I just wanted to finish it up here. So let's quickly jump into a notebook and get on with it. Okay, so this is the notebook we did the last time, at least when we did the binomial model. And I want to add fsolve. So from scipy.optimize import fsolve because we're going to need that, and I just want to pull it in because I will forget about it if I don't do it now. Fsolve, there we go. So the basic idea was we have the stock price at some time, we'll call it T0, and then we assumes it moves up with a probability P, an amount U, and ends up in this node, or moves down by an amount D, again with a probability 1 minus P, ends up here. And if we know, if this happens to be expiration, we can figure out what the option price would be, because obviously if it's out of the money at expiration, it's worthless. It's worth 0. If it's in the money, it's just whatever the intrinsic value is. And then from there, we can back out the option price at the previous node. This was specifically for calls, but the same thing would hold for puts. It's basically the expected value of the call discounted by the risk-free rate. And from there, you can extend it to a multi-node or a multi-layer type of thing easily enough. So you can figure out the call price for this node based on these two, the call price for, or the option price for this node based on these two, and so on, until you work backwards and fill up the entire tree. So down here, we basically implemented this. What I'm going to do now is shut off the recording and copy this part here, which actually does the calculation, and basically wrap it in a function so that we can make use of it for fsolve, or from within fsolve. So just to put a kind of a marker, division marker between this, I'm going to say this cell is, and this cell and below is going to be implied volatility calculation. Okay, so I edited out the actual part of doing this, and I added this where you could type in the contract type, be it a call or a put, and then down here, where is it? Oh, here it is, up here, where we handle the calculation explicitly for the calls or puts, and it's just basically switching the subtraction order to figure out the intrinsic value of the option. So let's just run this quickly based on the numbers we used up here. So let me just grab all of these, come down here and paste them in. And we don't need to figure out the time steps because that's handled by the function. So, and for this video, I'm just going to keep time equal to 1 year, so we don't have to worry about rescaling the implied volatility, but that's straightforward enough to do. So now let's just come down here and let's say print binomial, and so it's sigma S0 KRT and 5 nodes, and I'm just going to do the call, which says set to which it does by default. So let's just run that. 14.7. Let's call it 14.71, and up here, what did we get? 14.71, same thing. So we are good to go. So I'm just going to actually just delete this and actually move on to the volatility portion of this. So remember back when we did this in the context of Black-Scholes, we said that mathematically it amounted to this here. So finding the value of x such that some function of x is equal to 0. It's called a root finding problem, or finding the zeros or roots of a function. And that our function was the Black-Scholes model for a specific value of sigma equal to 0. Well, or let me say that a different way. It's the Black-Scholes model as a function of sigma minus the actual option price set equal to 0. And likewise down here, our problem is just the binomial option model prediction as a function of sigma minus our actual price is equal to, and I forgot to put the 0 here, 0. There we go. So yeah. And again, when we did this in the context of Black-Scholes, we used Newton's method, but in this case, it's going to be a little bit more complicated, and you could probably work out some relationship, derivative of the option price with respect to volatility, in other words, the vega of this model, but that would be quite the pain, and I don't think I really want to do that. So fortunately, Scipy has the built-in ability to do problems like that with the function called fsolve, which is what we imported earlier. So really all we need to do is build code for this objective function here and just pass it into fsolve. So down here I've already done basically that objective function. Here's our binomial prediction price here. Here is, I use C0. This could be a put as well as a call, but I just use the variable C0 for the option price. It calculates this difference and sends it back. So let's actually do something with it. So why don't we just recycle the stuff we've done up here? Where did I put it? Oh, I think I deleted it. So let's just grab the similar things from up here. Copy, paste. And again, we don't need this line. And let's use the option price we calculated up here too. Where was it? 14, let's call it 14.72. So let's come down here, say C0 is equal to 14.72. And let's just do, actually before we do an fsolve, we need to gather all the arguments together, the additional arguments, which are S, K, R, and T, and N. And now we can call fsolve. So fsolve, objective function, or objective I think I called it. And we need to choose an initial guess, so let's just guess, I don't know, 25% volatility. And the args is equal to our args variable. And that should do it. Let's just see what we get. And it's not S, it's S0. Now what? We need to pass in C0 too. C0. 40%. What did we set it to up here? Where did we set it originally? 40%. Let me copy it the Black-Scholes functions that we did previously and just see how this compares to Black-Scholes. Okay, so these are the functions we used back when we were talking about Newton's method, just the Black-Scholes model for the call and put price, and I added the import, we need the norm.pdf, the density functions, the cumulative distribution functions. So those are pulled in, and let's just run these variables through the call price. So call price sigma. Let's just hard code it at 40%. So 0.40 S0 K R and T, and see what we get. See, we get a different call price based on the Black-Scholes than on the binomial. But if we come back up here, I assume this is just a function of the number of nodes we're using. So if we crank up the number of nodes instead of 14 point something, we should probably get something closer to the Black-Scholes. So let's just change the number to 50. And indeed, we get 15.2 something. 15.2 something. So that's the issue there. So yeah, we have basically agreement between our two different types of models. Yeah, and that's basically all I have for this video. Okay, quick and simple. So as usual, I will just upload this to GitHub. Next time, I think we're going to go into a little bit of a heavier subject, return to boundary value problems, and look at a method called orthogonal collocation to solve those boundary value problems. And then I've been kind of negligent and not done the second half of the shooting method boundary value problem type of video. So I want to get back to that. And then where we go from there, I'm not quite sure yet, but we will figure it out. So yeah, cool. Until next time, I will see you later.